بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف خلق الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. ما زلنا في سلسلة نظرية الأوتار سترينج ثيوري مقارنة مع نظريات علي يوسف، وها هي الحلقة 13 بعنوان اتفاقي مع نظرية الأوتار في أنه لا يوجد ما يسمى بالمادة المظلمة. في الحقيقة أنا قدمت فيديو في هذا الأمر، فيديو تشويقي في هذا الأمر، وكان قبل 3-4 فيديوهات من الآن، وتحدثت عن معادلة اتفقت فيها مع نظرية الأوتار في أو نظرية الأغشية، في أنه إذا تباعدت الأغشية فإن يحصل كسر للتناظر من U1 من SU2 ل U1، وبالتالي تتحول الفيزياء من نظرية يانغميل إلى نظرية ماكسويل. وبالتالي نظرية ماكسويل نحن نعلم أنها تظهر فيها القوى الأساسية الثلاث، ويانغميل لا تظهر فيها القوى الأساسية الثلاث، لأنه WZ تعطي الكتل، وأيضا WZ طبعا تعطي الشحنات، هذا صحيح، تعطي الشحنات وتعطي الكتل. لكن WZ لديها شيء غريب، WZ عبارة عن طاقة صرفاء، هي تعطي الكتل لكن عبارة عن طاقة. وقد كتبت كتابا في هذا، كتابا ما يسمى سميته adopting WKB semi classical approximation، أي تبني نظرية WKB أو ما تسمى السيمي كلاسيكال ابروكسيميشن. في هذا الكتاب ذكرت أنه عند الفضاءات القريبة من الذرات، من الذرة ومن البروتون وداخل البروتون، مثل الفضاء حول الكوارك، والفضاء القريب من الإلكترون وداخل الإلكترون، هذا الفضاء يسمى فضاء كثيف لأنه فيه طاقة عالية وكتلة صغيرة، جسيمات في ذلك الفضاء لديها كتلة صغيرة لكن طاقتها عالية. فWZ أخذت نفس المنحى عند التفاعلات في مفاعلات الهيدرونات الكبير، تفاعلات QCD والQED، نجد أن WZ لديها طاقة أعلى وكتل صغيرة. طبعا معروف أن الكتل WZ كتلتها عالية 82 ل 95 جيجا إلكترون فولت، لكن هذه ليست كتلة إنما طاقة، وبالتالي تعطي الطاقة للكتل، بالتالي تعطي طاقتها للليبتونات وتعطيها للكواركات وما إلى ذلك. فهذه هي حتى بوزون هيجز لديه نفس الخاصية. فالبوزونات هي عبارة عن جسيمات تسمى بحاملات القوة، تعطي طاقتها أو تعطي هذه القوة تتشكل في شكل كتلة. طيب ما الذي يجعل البوزون يعطي الكتلة، وما الذي يجعل الإلكترون والبروتون والليبتونات عموما والباريونات عموما تأخذ الكتلة؟ الأمر في نظرية لا يتعلق ب WZ، إنما يتعلق بشكل الفضاء، وهذا ما ستجدونه في هذا الفيديو. وأيضا تحدثت عنه في سلاسل سابقة بالمناسبة، تحدثت عن هذا الأمر في سلسلة الشيطان يقبع في التفاصيل والملاك يقبع في التفاصيل والتسلسل التاريخي، والأخيرة النسبية العامة وعلم الكونيات بالجزئين وها هي السترينج ثيوري تخبر بنفس الأمر يحدث. وغريبة لأنه ما يحدث في حسب نظريتي في التفاعلات الصغيرة يحدث داخل الثقب الأسود. بالتالي نظريتي استطاعت أن تربط بين الفضاء داخل الثقب الأسود بالتفاعلات الصغيرة عند مفاعل الهيدرونات الكبيرة. ولهذا أقول للمرة الثانية والثالثة أن نظريتي يمكنها أن توصل العلماء وتوصل البشرية أنهم كيف يعملوا تجارب لنظرية الأوتار على أحجام كبيرة. إذا اتبعوا نظريتي فإنهم يستطيعون أن يعملوا تجارب لنظرية الأوتار على أحجام كبيرة. تعالوا إلى الفيديو لنرى كيف أن يعني نظريتي استطاعت أن تتفق مع نظرية الأوتار في موضوع المادة المظلمة. طبعا الطاقة المظلمة تحدثنا عنها في كثير من السلاسل السابقة، خصوصا النسبية العامة وعلم الكونيات، سلسلة النسبية العامة وعلم الكونيات. لكن هنا أيضا نظرية الأوتار أو نظرية الأغشية تتفق معي تماما في أنه لا يوجد مادة مظلمة، إنما هي مادة عادية، لكن الفضاء يلعب دورا كبيرا ويجعلها تظهر وكأنها مادة مظلمة. تعالوا إلى الفيديو.
Have a mass, sure. So let's talk about what should be the mass of a deep brain if it's a dynamic object. Okay. So here there's a very simple and intuitive answer. So on the deep brain, there are many open strings. In principle, there are the infinite number of open string excitations live on the deep brain, and each of them can be considered, say, as a space-time field living on the deep brain, etc. So the actual definition for the mass of a deep brain is that this should be the energy of a deep brain with the essentially should be the ground state, the energy of the ground state of the deep brain. The energy of the ground state of the deep brain should be corresponding to the energy of the deep brain. None of those strings are excited. Okay? Then that should corresponding to the vacuum energy of open strings. Okay. So this is
طبعا ديبرينس يمثل الفضاء الديفكت اوف سبيس، ولا الكيرفد سبيس بالنسبه للفضاء ثنائي الابعاد ايضا يعتبر ديفكت بالنسبه للفضاء ثنائي الابعاد، يعني شيء غير مقبول. وبالتالي الكيرفد سبيس يمكن اعتباره هو زيرو بوينت انرجي بالنسبه ل يعني مثل البرين بالنسبه للفضاء ثنائي الابعاد عند تلك المنطقه. فبالتالي يمكن اعتبار انه الكيرفد سبيس له عدد كبير جدا من الفضاءات المسطحه تعتمد على الكيرفد سبيس، سواء كان الكيرف في بداية الكيرف أو في نهاية الكيرف. فكل هذه الفضاءات المسطحة كل واحدة لديها زيرو بوينت انرجي لوحدها، ومجموعة يعطينا الهاملتونيان كما قالت نظريتي، مجموعة يعطينا الهاملتونيان. يعني نجد أن الهاملتونيان أو الطاقة الحركية للجسيمات تزداد من أول الفضاء منحنى. يعني مثلا على سطح الأرض نقول أنه مثلا على بعد كذا كيلو من سطح الأرض يبدأ الفضاء بالانحناء، وبالتالي إذا سقط الجسيم من تلك المنطقة فإن الهاملتوني يزيد أو الطاقة الحركية تزيد. وهذا ناتج عن ماذا؟ ناتج عن زيادة الكيرف وزيادة الزيرو بوينت غير ثابتة، زيادة بالزيرو بوينت كل مرة، لأنه الزمن حول الأرض ليس ثابتا، وإنما الزمن هو متغير بسبب التايم كونتراكشن، لأنه نحن على سطح الأرض ننظر عن طريق ما يسمى بالتايم كونتراكشن، وتظهر هذه التايم كونتراكشن في السرعة، زيادة السرعة. فبالتالي الزيرو بوينت غير ثابت، ويعتمد على الكيرف سبيس، ويعتمد على اللوكيشن بالنسبة للسيستم في الكيرف سبيس كما قالت نظريتي.
Very intuitive definition, and obviously makes sense. So we can write the mass of a deep brain, say DP brain, say as the tension, which is the mass per unit volume times the total volume, okay? And this should be equal to the vacuum energy of all the open strings, okay? So say each open string excitation corresponding to a field. You have a tachyon, you have gauge field, you have massive scalar field, and also infinite number of massive fields. All those fields, they have vacuum energy. So you need to sum all of them together. Then that would be the sum of those vacuum energies would be the mass of the deep brain. Okay. So this can be achieved just by doing the vacuum diagram of open strings. So we describe in the closed string case. So if you want to find the vacuum energy in the closed string, you just sum of all possible. So this will be just the vacuum diagram. Of open strings. In other words, so the difference between the open string is that open string have boundary, and closed string are closed. Closed string are closed. Okay, so that means that sum over all two-dimensional surfaces with at least one boundaries. But no external strings. Okay, but no external open strings. So this means, this is the natural definition of the vacuum diagram, so as we would do in, and we will do.
هذا ما توصلت إليه، هذا نفس الأمر الذي توصلت ذكرته الآن. الديب برين يعتبر ديفكت ويعتبر كيرفد سبيس، والكيرفد سبيس يعتبر ديفكت، ومجموعة السبيسز الفلات سبيسز اللي هو 0 بوينت أو 2 دي سبيسز يعطينا الطاقة الكلية ويعطينا التسارع بسبب الجاذبية، أو يعطينا زيادة الطاقة الحركية بسبب الجاذبية. هذا ما توصلت إليه.
In the Euclidean path integral, so you can do this in the Euclidean path integral. When you sum over all in the case when you need to sum over all surfaces, in some sense the only way we know how to define such a sum is to do the Euclidean path integral. Okay? And this sum essentially just you. So previously we talked about the vacuum energy of the closed string. You sum over all possible closed surfaces, say of different topology. So here again you sum over all possible surfaces with at least one boundaries. So the simplest surface with one boundaries is a disk. Okay. So now you have to, the difference with closed string case, now you have to sum over surfaces with boundaries. And so the simplest one would be a disk. And the next, there would be annulus. Would be now you have two boundaries rather than one boundary. And etc. You can consider more and more complicated diagrams. Okay, you can consider more and more complicated diagrams. And the way to weight those surfaces exactly the same as before is that you have this G string, then to the power minus chi, and the chi is the Euler number. Okay, just exactly as we described before. And the Euler number, now to apply surfaces with boundaries would be, so previously Euler number is 2 minus 2h. So h is number of genuses or number of holes. So now you also need to include the number of boundaries, which I call B. Okay, so when you include the boundaries, then that will change the Euler number, and also change the weight of the for each such diagram.
هنا طبعا هذه المعادلة أيضا فيها شيء غريب جدا. اتش تعتبر جينيس، يعتبر يعني الهول، وبالتالي كلما زادت الهول كلما زادت زادت كل ما زادت الاتش وكلما نقصت الاكس كلما نقصت الاكس. وبالتالي نجد أن مع زيادة الهول فإن الجي يكون بشكلها الموجب وليس السالب، والجي أصلا تؤول إلى زيرو داخل الثقب السوداء. طبعا داخل الثقب الأسود مثل بالمناسبة مرة ثانية داخل الثقب الأسود هو مثل الفضاء خارج الثقب الأسود بدون كتلة، وبالتالي نتوقع أن داخل الثقب الأسود أن اتش تنقص. لماذا تنقص؟ لأنه داخل الثقب الأسود هو مثل الفضاء الخالي من الكتل، والكتل هي سبب الاتش، لأنه ترفع الهاملتونيان، الاتش ترفع الهاملتونيان ترفع الطاقة و يعني تجعل الستيتس قريبة من بعضها البعض، وبالتالي نتوقع أنه داخل الثقب الأسود يشبه الفضاء الخارجي من غير الكتل، وبالتالي اتش تنقص. لكن عكس أنه بالنسبة للملاحظ الخارجي ويرى الثقب الأسود فإن يرى عبارة عن هول، وبالتالي اتش تزيد. يعني عليكم أن تعرفوا الفرق بين الملاحظ الداخلي والملاحظ الخارجي. الملاحظ الخارجي يرى هول، وبالتالي يرى اتش تزيد، وبالتالي يجد أن جي اس تزيد. وهذا ما نراه في إشعاع هوكينج، نرى هذا. لكن بالنسبة للملاحظ الداخلي العكس تماما، الموجود داخل الثقب الأسود العكس تماما، اتش تنقص وبالتالي جي تنقص. هذا بالنسبة ل اتش. تعالوا نشوف البي.
You can also add handles here. You can also add genesis to the disk. Then you will corresponding to a you can also add age here. Okay. So according to this counting, then this would be counted as GS minus 1, and then this have only this one have 0 holes and 1 boundaries. So this is 2 minus 1. So this is 1. So this is GS to the power -1. And this one have low hole, but 2 boundaries. 2 minus 2 is 0. So this is called the 1 to the power GS to 0. And then you have higher diagrams. You have higher surfaces than with all positive power of G. Okay, GS.
طيب بخصوص البي نجد أن البي هي عبارة عن باوندري. بالنسبة للملاحظ الخارجي يرى باوندريز للثقب الأسود، لكن الملاحظ الداخلي يرى ثقب أسود لا نهائي، لأنه الزمان يعتبر مكان والمكان يعتبر زمان، فالثقب الأسود لا نهائي. بالتالي نجد أن بي يساوي 0 في داخل الثقب الأسود، وخارج الثقب الأسود بي لا تساوي 0، يعني بي و اتش لا تساوي 0. أما داخل الثقب الأسود بالنسبة للملاحظ داخل الثقب الأسود يرى أن بي يساوي 0 و اتش يساوي 0، وبالتالي الفضاء داخل الثقب الأسود مثل الفضاء خارج الثقب الأسود، وهذا ما ذكرته نظريتي.
Yes.
What about like a Mobius strip? That has one boundary.
Right. Yeah. So the Mobius strip is a very good question. A Mobius strip is unoriented surface. So here we consider oriented string. Yeah. You can consider unoriented string. But most principle, most what we said apply to that case. It just we have to worry a little bit about orientations actually. Yeah. So we don't go.
But that really contribute to the vacuum energy.
Hmm?
Well, the Mobius.
Yeah.
contribute to the vacuum energy.
Will. Yeah. In the case when you have when you have unoriented string. Yeah.
But is
It
there
may
any
contribute.
restriction was say?
هناك شيء آخر أيضا كما ذكر في الفيديو السابق أن جي يمكنكم الذهاب إلى الفيديو السابق، أن جي تتناسب مع الاكسبكتيشن فاليو بالنسبة لفاي، يعني جي يساوي اي او سي اكسبكتيشن فاليو بالنسبة لفاي، وفاي هو التايم دايليشن أو الداليتون بارتيكل بشيء معين يسمى الداليتون. اذهبوا للفيديو السابق لهذا مباشرة وستجدون هذا الأمر. طيب ذكر المحاضر شيء غريب في هذا الفيديو، ذكر أن جي صغيرة جدا بالنسبة للسترينج جي صغيرة جدا، ولكنها في نفس الوقت تتناسب مع يو سي الجسيم الدالتون، وهذا يؤدي إلى تناقض. لماذا؟ لأن الجسيم الدالتون موجود فوق فوق البرين، هذا الدالتون هذا يتناسب مع جي. مفترض أنه كلما زاد الدالتون كلما زادت الجي وليست تنقص، وذكر أن هذا تناقض لم تستطيع حله نظرية الأوتار. وأنا ذلك الوقت ذكرت شيئا عن أننا مفترض نأخذ في الاعتبار كما أخذنا التايم دايليشن نأخذ الديستانس دايليشن، وهذا مفترض أن يكون في الاعتبار. لكن هنا الإجابة لماذا جي صغيرة في السترينج ولماذا كبيرة؟ جي صغيرة في السترينج لأنه عند الأبعاد الصغيرة فإن التايم لن يكون دايليشن، لا يحصل له دايليشن، إنما كونتراكشن عند الأبعاد الصغيرة، وبالذات أبعاد بلانك، لأنه التايم دايليشن يظهر عند حدود 10 أس ناقص 27 متر، لكن أبعاد بلانك يعتبر التايم دايليشن كونتراكشن. السبيس أيضا يحصل له كونتراكشن، وبالتالي يكون الفضاء لهذا يكون الكوبلينج كونستانت. طبعا جي اس هي الكوبلينج كونستانت للسترينج تكون صغيرة. لماذا؟ بسبب أن فاي الدالتون يكون أقل ما يمكن، اللي هو الدالتون بارتيكل يكون أقل ما يمكن. وهذا بسبب ماذا؟ وهذا بسبب أن الدالتون هذا يعبر عن التايم دايليشن، ونحن نتكلم عن التايم كونتراكشن. يعني نظرية أجابت على هذا السؤال. فداخل الثقب الأسود هو التايم كونتراكشن، وخارج الثقب الأسود أو عند الأبعاد الصغيرة يكون هناك تايم كونتراكشن، خصوصا عند أبعاد بلانك يكون تايم كونتراكشن، وبالتالي الدالتون تكون صغيرة، وبالتالي الجي اس يكون صغير. الجي اس يكون صغير بالرغم من أنه هو أوسي دالت أوسي فاي. فأيضا هنا نجد الإجابة من هذه الصورة أيضا إنه كاي بالنسبة ل جي اس، طبعا جي اس أس ناقص كاي، فكاي نجده هنا كبير لكن هناك علامة ناقص، فبالتالي هذا ما يسبب الجي اس يكون صغير، لأنه كاي عبارة عن 2 ناقص 2 اتش ناقص بي، وبالتالي بي يساوي 0 و اتش يساوي 0 داخل الثقب الأسود أو عند الأبعاد الصغيرة. طبعا الأبعاد الصغيرة أبعاد السترينج نجد أنه نو باوندري، ما في باوندري عند أبعاد السترينج، بحيث أنه التايم كونتراكشن يكون عالي والسبيس كونتراكشن يكون عالي، فربما يكون ليس هنالك باوندري. أبعاد صغيرة 10 أس ناقص 70 متر مربع، ألفا يعني ألفا برايم يساوي هكذا، فبالتالي لا يوجد برايم ولا يوجد باوندري. وأيضا الاتش لا يوجد اتش اللي هو جينيوس الذي يعتمد على الهول، لا يوجد هول عند الأبعاد الصغيرة إلا بسبب كتلة السترينج ذات نفسه. كتلة السترينج ذات نفسه هي التي تعمل باوندري، هي تعمل الهول وتضع نفسها في محاربة مباشرة مع الفضاء صناعي الأبعاد غير متناظر. فبالتالي هذا يفسر لماذا جي اس ناقص اكس جي اس صغيرة. لماذا جي اس صغيرة؟ بسبب هذا الأمر، أن السترينج لا يوجد لديه كتلة، والشيء الآخر أن الاتش يساوي 0 لأنه لا يوجد هول، وأن البي يساوي 0 لأنه عند تلك الأبعاد الصغيرة فإنه التايم كونتراكشن والسبيس كونتراكشن يكون عاليا. فهذا أيضا تفسير تقدمه نظرية علي يوسف. طيب تعال نواصل.
It's on this degree we have or not have our.
No, here we all consider oriented surfaces. We all consider oriented strings. Yeah, we have not talked about unoriented strings.
But no restriction in principle.
Yeah, you can. Just it's actual a technical complication. I don't want to go into right now. Yes.
So we think of like vertical axis as time, so the disk would be a string kind of nucleating and propagating.
No, there's no. This is a Euclidean, and you can think time as whatever you want.
Right, but still, so the disk would be like a nucleating open string that then propagates and then kind of disappears. Right?
Yeah. For example, this open string you can consider. Yeah, just say. Heuristically, you may be able to think some kind of a single string just rotate, for example.
Like rubber?
Yeah, for example, I just say a single. Yeah, I'm just saying it's hard to interpret as a time now. Yeah, but the time would be in this direction would be a periodic time. Yeah, if you think from that point of view. Yeah. Yeah, but the good thing is that when you go to Euclidean, then what you call time and the spatial direction then become obscure. You can it depends on your convenience.
This in the center, is that a genus?
No, the center is completely smooth.
It's not like a torus.
No. The disk is a disk. Disk is not a torus.
But I mean, there's a.
You're talking about this one.
Yeah.
Oh. This one is annulus. This one is annulus. This is a flat surface.
So the inside and outside of the other.
They're different. If you identify this and that, then that become a torus. Yeah, that become a torus. Yeah, when you identify this one, that one, then that become a torus. Yeah, then you get rid of the boundaries. Yeah, when you identify them, then there's no boundary anymore because that become a circle.
Yes.
Good. So that means if I have weak coupling, that means when GS is much, much smaller than 1, which is the cases we can only consider, because if you have GS order 1, then you have some infinite number of diagrams, then we don't know how to deal with this. So at weak coupling, when GS is smaller than 1, then the brain tension, then the D brain will be always scale with a string coupling at 1 over GS because of that, because this term will dominate, and then the energy should be 1 over GS. Okay? So this is a very important result. So the mass of the D brain is actually 1 over GS. Okay? So an undimensional ground you can just essentially write down what's the tension of the D brain, because the only dimensional parameter is alpha prime. So the dimension of the D brain should be, so this is mass per unit volume. So if you have a p dimensional volume, then that would be p plus 1. So the mass dimension of the tension would be p plus 1. So just on dimension ground, I can write GS because it's 1 over S, alpha prime 1/2 p plus 1. Okay, so that gives you the right dimension, and then you can have some numerical constant, which you need to determine. Is some numerical constant. Which you can determine in string theory, or say by doing that path integral. Okay. Any questions about this? Yes.
Do these open string vacuum diagrams have any interpretation as like half of a closed string diagram? So like if you put two disks together, you get like a sphere.
Right. We will talk about this in a minute. Yeah. Yes.
What's the logic of that decomposition of the powers of G, right? The disk G minus 1 and...
Oh, yeah, just come from this formula. As we discussed before, the weight of different topology is always weighted by some constant times to the power of Euler number. And now the Euler number, if you have surfaces with boundaries, then the Euler number depends on the number of boundaries. And then you can just work it out. Yeah. Okay, so this is based on simple. Any other questions?
Here as the one, remember when you calculate the mass of the string?
Yeah.
We have an A0 term where there is no excitation. So.
Sorry, say it again.
So when we calculate the mass of the open string, and there is an A0 term which is.
Oh, so then that's completely different. So that A0 we considered before is the 0-point energy for the oscillation modes on the string. So we are considering so that A0 is that we are considering this string. We are considering this string, and the 0-point energy for the oscillation mode on this string. But here we are considering the 0-point energy, not the string. We are considering the 0-point energy of the D brane. And the 0-point energy of the D brane would be to write down the vacuum energy of all the fields living on the D brane. And all the fields living on the D brane corresponding to all the, so each string excitation becomes a field on the D brane. And so that's corresponding to sum over that. And that's then in turn corresponding to sum over this kind of surface. So this, Any other questions? So there's an alternative way to think about how to compute the D brane mass or energy as follows, which is actually extremely instructive. There's an alternative way of doing it. So let's consider just D brane. So consider the interaction between the two D branes. Okay, so let's consider the two D branes separated by some distance. Okay, and then they have a mass. Then they will interact gravitationally. In particular, in the weak coupling limit, they're pretty massive. They're very massive because it's 1 over the G string. So when when G string is small, which is the only regime we are working with, so the D brane is very heavy. Okay. And so you can ask, what is the gravitational attraction between the two? Okay, what is the gravitationally? In particular, in the weak coupling limit, they're pretty massive. They're very massive because it's 1 over the G string. So when when G string is small, which is the only regime we are working with, so the D brane is very heavy. Okay. And so you can ask, what is the gravitational attraction between the two? Okay, what is the interaction between the two? And we know that at no energies, say if the two D brane are not excited, if their distance are very far apart, then the leading interaction between them just comes from the massless modes. Because only massless modes mediate long-range interactions. Okay, and so interaction between them just come from graviton or this dilaton. Okay, essentially just corresponding to small number of massless closed string modes. Okay, only those massless modes will contribute, and because the massive mode only contribute short range interactions.
Why not the vector mode in open string?
No, vector mode of vector mode of open string only live on each brane.
But we can have open string like.
No, I will talk about separately. Just wait a little bit. So if I think purely from the ordinary gravity point of view, not from string theory point of view, I have two massive objects. I want to look at the interaction between them, and then the interaction will be proportional to Gn, say their mass. So if I factor out the volume factor, it would be just Gn Tp squared. Okay, so this essentially is the gravitational interaction between the two. And from the string theory point of view, such a diagram corresponding to you exchange your closed string. So this diagram corresponding, say suppose you have a brane 1, brane 2, brane 1, brane 2. So this has a picture that brain 1 will emit a graviton, then absorbed by the other brain, and then that's how we measure the Newton's force between them. Okay, and translate to the string theory picture. This corresponding to one of the D brain emit a closed string, and then absorbed by that by the other D brain. Okay, and when you go to the low energy limit, which only match this mode matters, and then become this picture. Okay, and so this is a string theory version of that diagram. So now, essentially, what you need to do this, to calculate this thing in the string theory, is to calculate this cylinder diagram. So from the string theory point of view, now what you need to consider is to consider such as to do path integral on the topology of a cylinder. Okay, and with one boundary on the brain 1 and the other boundary on the brain 2. Okay, and so this corresponding to exchange, say, of a gravity exchange of a closed string in this direction. Yes.
How can what's the mechanism for the brain emitting a closed string, or equivalently on the other picture, like why can it emit graviton?
And it's coupled to graviton.
So like, how do we introduce the coupling? How do we introduce the coupling? I mean, we introduce them as boundary conditions for open strings.
Yeah.
So does that naturally introduce?
Yeah, this comes
coupling,
from
or?
no. This is what I'm writing here, and this diagram you emitting a closed string, corresponding to look at the cylinder, and with one boundary of the cylinder on the location of the one D brain, and the other boundary of the cylinder on the location of the other D brain, and then you just integrate over this surface, and then that will give you the graviton exchange. Now that will give you the closed string exchange between the two.
So the coupling of the closed string to the brain kind of naturally arises?
In the boundary condition imposed here. So you impose this closed string to initiate it from. So you impose the boundary condition here, so that that this closed string starts from brain 1, and then end on brain 2, and then you integrate over all surfaces with cylinder topology. Okay.
We know the interaction constant for closed string is the G closed, but it's the same here.
No, so that's what I'm going to talk about. Yeah. Is this clear? Okay, so now I'm going to mention two things. First, as I said before, whenever we do some calculations, we often do analytic integration to the Euclidean signature. Okay. So now we will do the same. So when we do this, when we do this calculation, we have a closed string start the location of the brain 1 and move forward in time to end on the brain 2. So this is a simplest diagram. You can also add some holes here. You can also add some holes here, and then that corresponding to higher order diagram structure. So now there's not worry about that. Just a simplest diagram. Yes.
Was it time dimension inside brain? You can define time dimension as one of the dimensions that we inside brain.
Right. Yeah. But this is not the space-time time. Let me call it tau. This is a watch time. This is a virtual time associated with this graviton. Yeah. So essentially, I nucleate the closed string here on this brain, and then propagate, and then absorb by the other brain. Okay.
Can you also think about this as like an open string?
Yeah. 1 second. I'm going to explain. So now there are two remarkable things about this diagram. First, this is a cylinder diagram, and this is a diagram with two boundaries, because you have to emit a closed string from here, And so you have one bound, you have an initial a closed string, then you have a final closed string. So this is a surface with two boundaries, but with no holes. And if you calculate the chi, so this would be 0, then that means this diagram is gs to the power 0. Okay? And then from here we know that, and then this from string theory point of view will be gs to the power 0. And so this is another way to see that the TP should be 1 over G string. Okay? 1 over the G string. Okay, because we have said before that the G Newton, so we explained before G Newton will be order of GS squared. Okay? G Newton is the G string square. So do you remember G Newton is G string square? Good. But there's something remarkable about this diagram is that you can also view this diagram. So right now we see it from this direction. Now we can also view it from the other direction. View it from this direction. So now try to think about this direction as a time, and this direction as a sigma. So right now we are seeing this as time, worksheet time, and this as a sigma. Okay, this is a closed string. So now think about you viewing this direction and this direction as a time. And then this is an open string which ends with one end ending on brain 2 and the other end ending on brain 1, and then going in a loop. Okay, so this is a one loop open string. So even though this is the tree level exchange in closed string, so here is the tree level exchange in closed string. So here is one loop in open string. Okay? So this tells you the same process. The same process. You can really view it from two perspectives. You can really view it from two perspectives. From one perspective, is the standard point of view, is that we exchange some closed strings. Say we exchange some graviton, some massless particles, some particles between these two. But there's another way to think about it, is we say R between these two branes, because we have two D branes here, and because D brane corresponding to places open string can end, then I can have open string, then I have open string connect between them. And this one loop open string is essentially corresponding to the vacuum diagram of those open strings connect between them. So when you add the vacuum energy of all those open strings between them, ending between them, then you effectively calculating the interaction between the two D branes. Okay? So we have.
طبعا هذا الكلام مهم جدا جدا في غاية الأهمية، لأنه الزيرو بوينت انرجي بالنسبة للغشاء الفوق ليس مثل الغشاء التحت، نسبة لأن الأبعاد تزيد، فبالتالي نجد أن الزيرو بوينت انرجي أو الفاكيوم انرجي للغشاء الفوق هو أعلى من الغشاء التحت، وبالتالي هذا سيؤثر في ماذا؟ هذا يؤثر في التفاعل.
Have two completely different perspectives to look at the same process. And this is very, very deep and profound. Deep is profound. Because that means the process which you can think from closed string perspective can be fully understood in a different way from the open string perspective, in the completely equivalent way. Okay? And this is normally called the channel duality. So it's a very simple geometric fact about two-dimensional surfaces, but physical significance is very profound. Yeah, well, 1 second, let me finish. And this is precisely related, this is precisely the string theory origin of the holographic duality or the ADS-FT we are going to see in a couple of lectures. Just because of this simple geometric picture. Okay, just because this simple geometric picture. This side is gravity, and the D-brane is about the field, is about the gauge theory, and then we see gravity to be equivalent to a gauge theory. Okay, and so that's something we are going to see later. Yeah.
Oh, so if it, so you said like the dynamics of a closed string can be fully understood by the open string.
Yeah.
But what if say it's a closed surface formed by a closed string? How can you interpret it?
Right. Yeah. No, I'm talking about this particular diagram.
Oh, very
No. I'm just saying this gives you a hint of something very profound.
Okay. And one more thing that why is it GS?
Huh?
Why is it GS?
No, this is a surface of two boundaries.
Oh, but that.
No,
That is for open string.
No, chi is for everything.
Oh, okay.
No, chi is for everything. It doesn't matter open and closed string. This is a universal formula. This is open. So open string just means impose the boundary condition on the open string. The topology is the same. Yeah, when you sum over the topology is the same. Yes.
Why do you call it one loop string? What is the root?
Yeah, because this is an open string. So this is the open. Yeah, think from this point of view, this is an open string ending on brane 1 and brane 2, and then you go around once, go around in circle. So this is a one loop.
What's the free momentum for instance?
What is this? What is this? This is a one loop if you have a particle, and so you have a string, then you go around the circle. This is the one loop. Yeah. And indeed, in this when you sum over such surfaces, you will need to sum over all possible momentums, etc. So the field theory momentum is one of the modes you have to sum over. So when you do path integral over surface of such topology. Yes.
But once you go to strings connecting different branes, your quantization conditions change and wouldn't that?
Yeah, we will talk about that. Quantization condition almost does not change. We will talk about that. Yeah. We'll talk about that in a little bit. But right now it's just intuitively clear. You have open string connect between them, and then just go around. You have open string connect between them, you can just go around the circle. Okay?
But this correspondence doesn't count the tree level diagram for open string.
Count what?
Can it be generalized to tree level open string?
No, tree level. No, this does not have to account for the tree level open string.
Tree level open string contribute to the interaction.
No, that tells you that this tells you. Yeah, here I mean, only talk about this diagram and just say this hints that there's certain closed string process can be completely described by the open string. And what? So if we want to extrapolate, is that open string is a more fundamental description, because the tree level diagram in closed string can be described by the open string, and now if you can generalize, and then maybe everything closed string can be described by open string, but you don't want to do it in the opposite way. The open string just open string. Yeah. Okay. Good. Any other questions?
But once you go higher dimension in the, when you need tree level of closed string, can be distinct.
Yeah, things become more complicated, but things become more complicated, but the similar picture can exist. Yeah, will exist. Yeah. But nobody have made it work. Nobody have made it work at the full string theory level, say to construct the whole closed string theory from the open string theory. Nobody has made it work. But there are many such kind of indication from the geometry of the surface point of view. Okay.
ربما سمعتوا هذا الكلام. ما في إنسان قدر يعني يقدم full description للسترينج ثيوري إلا عن طريق الجيومتري بهذه الطريقة. وهذا بسبب أنه يعني ربما أقول ربما معادلة أو نظرية تعريف بس أنا تقدم هذا الفول ديسكريبشن أو ربما ستعطي نظرة أعمق للسترينج ثيوري بهذه الهيئة التي أشرحها، وربما هناك هيئات أخرى أنا لا أعرفها.
Now let's talk about the lexeme, the strengths of open string interactions. Before I do that, now it's a good place to go back to examine what we discussed at the end of last lecture. Now it's a good time to go back to talk about what we did at the end of the last lecture. So in the last lecture, at the end we described that one can work out the low energy effective action, say, of the massless modes on the D branes. Okay, so the massless modes on the D brane are the gauge fields along the D brane, so alpha from 0, 1 to P, and then the scalar field and A label all the perpendicular directions. Label all the perpendicular directions. So you can write down effective action for them. So I mentioned if you work out things carefully, then you find the prefactor is actually just the brane tension. And if nothing is excited, if nothing, P plus 1, if nothing is excited, then you just have the vacuum energy, so you will have a 1. Okay? And so this is just the brane mass. The total brane mass, this is ET. Okay, this is ET. Okay? So if nothing excited, then you just have the 0 point energy, which is TP. Okay, TP times the volume. But now if you say also have gauge field, then based on general argument, you must have the Maxwell. And now if the scalar field are excited, then you also have the action for massless scalar field. The action for massless scalar field. Okay. And then we mentioned that, for example, you can consider a special case. Say, suppose A alpha is not excited, but the scalar fields, they move in a coherent way, the same at all points on the D brane, just phi A. It's a function of t rather than x. So phi in general. So in general, both. So suppose the brane coordinates are x0 and the p. So in general, A alpha is a function of x0, xp, and phi A is x0 and xp. Okay, so so they describe that you can have arbitrary profile on the water volume. So, but suppose, say, let me consider the uniform situation, which I only consider every point have the same behavior for phi, and then this S just become 1/2 dt, just become dt m d brane plus 1/2 m d brane phi dot square. Okay. So this is precisely the motion of just some massive object. Okay. It's the motion of some massive object. and m is m is just this guy. So if nothing depends on the spatial coordinate, then the integration of the spatial coordinate become the volume. Then combine the volume with that become the mass, and then just become that. No, I think this is minus sign. This is plus sign. Okay. So as I mentioned, this is another way to see that the D-brane become dynamical. And in particular, this phi describes the motion of the D-brane. So in fact, this result can be much strengthened. But I will only quote the results. I will only quote the results. It turns out, for D-brane, say with constant, so suppose the D-brane move with a constant velocity. So now you can also have a motion in the spatial direction. So you have a constant of this, and f alpha beta. So suppose you also excite, you can also excite the gauge field, but the field strength is constant. Okay. Or these quantities are small. They don't have to be strictly constant, but at least they're still the derivatives small. In such a situation, one can actually sum all the higher order terms from string theory corrections. So this is just a low energy, just like a field theory. But in such a situation, you can actually sum over infinite number of higher order terms. And what do you find? You find so-called, when you sum over all infinite number of higher terms, you find so-called Dirac-Born in-field action. You find that this effective action become like this. So this is very elegant result, so I just want to mention it. Okay. You can actually sum into this form. So if you you can sum into this form, and this G alpha beta is the following. Okay. So let me just explain a little bit the physics of this the physics of this formula. So let's first consider the case the phi is not excited at all, just phi equal to constant, say for example. Then this term vanishes. Then this G alpha beta just become eta alpha beta. Okay? And now you just have a square root, say your Minkowski metric plus f alpha beta. Yeah, forget about this 2 pi alpha prime. And this is just some dimensional factor. And then you just have eta alpha beta plus f alpha beta. And then you value the determinant. And suppose when f alpha beta is small, so when alpha prime times f alpha beta is small, then you can expand it in powers in f alpha beta. Then it's a simple exercise, but instructive exercise. Then you see that precisely reproduces the Maxwell term. Okay. But this will give rise to higher nonlinear terms. There will be a higher order nonlinear terms. So this can be considered as a generalization, nonlinear generalization of the Maxwell theory. It turns out actually this theory was considered in the 30s by this guy Born and Infeld. Yeah, Bohr and infield, and they actually maybe 30s or 40s. Yeah. Anyway, prehistory. Yeah. They invented as a way to avoid. They want to avoid the singularity of the Maxwell theory. So in the Maxwell theory, if you have a charged particle and then the location of the charged particle, then the field due to that charged particle is singular at the location of that particle. And so they want to avoid that singular behavior, so they invented this point field action. And for many years, this action does not have any applications, but if you invent something nice, it will find its use. Yeah, just like in this movie Jurassic Park, the knife finds a way.
طبعا ربما سمعتم هذا الكلام العميق جدا جدا. فذكر المحاضرة أنه هذا الحد تم اختراعه من أجل أنه يتحاشوا السنجولاريتي، ولم يجد هذا الحد أي تفسير أو لم يجد أي يعني منتوج فيزيائي للدخول فيه حتى جاءت السترينج ثيوري وتم ادخاله في هذا. الشاهد في الأمر أنهم أرادوا أن يتحاشوا أو يتجنبوا السنجولاريتي، وهذا يعني أن الفضاء الثنائي بعض غير متناظر فيه مفهوم عميق جدا دواخلهم في ذلك الوقت. منهم دينغتون حاول بمعادلته المشهورة أنه يتجنب السنجولاريتي وأوجد نظرية علي يوسف. يعني أنا أقول أن نظرية علي يوسف كانت بدايتها من دينغتون وكروسكال، ثم جاء علي يوسف ليكملها. فهذا الحد من الثلاثينات والأربعينات لم يدخل عليه شيء إلا في نظرية الأوتار، عندما أصبحت السنجولاريتي مهدد طبيعي أو الكتلة أصبحت الكتلة مهدد طبيعي للفضاء الثنائي الأبعاد، وهذا شيء طبيعي جدا جدا أن يدخل هذا الحد وجميع الحدود التي تم إهمالها في ذلك الوقت. وهذا ما يدل على طرد الكتل، لأنه FAB هي عبارة عن تنسور الكترومagnetic تنسور، ويمثل طاقة، طرد الطاقة. هذا عبارة عن طرد الطاقة، يعني هذه المعادلة تخبرنا عن طرد الطاقة، وهذه المعادلة تخبرنا عن طرد الكتل. هذه المعادلة تخبرنا عن طرد الكتل، وهي شبيهة جدا بمعادلة الكوفاريانت أو الجيج انفاريانس. جي يساوي إيتا هي الديريفيتيف في الفضاء المسطح اللي هو فضاءنا نحن، وزيادة عليه أو نقول في الفضاء المسطح حتى ما فضاءنا نحن، يمكن نقول فضاء مسطح متعدد الأبعاد، لكن جي تعطي فضاء منحني. ومن أجل أن نعبر عن الفضاء المسطح بدلالة الفضاء المنحني لابد أن نطرد كتل من الفضاء المنحني، ويمثل هذا الطرد في بارشر ألفا بالنسبة لفاي A. فاي A تمثل بارتيكل ماسيف بارتيكل، لأنه يعتبر الديليتون. هذا يعني لديه كتلة، وهذا يعبر عن طرد الكتل. يعني هذه المعادلة تعبر بعمق جدا عن مبدأ علي يوسف أو نظرية علي يوسف في موضوع الصراع بين الفضاء الثنائي الأبعاد والرباعي الأبعاد والكتلة، وموضوع آليات الفضاء الثنائي الأبعاد في الدفاع النفسي. طيب تعالوا نواصل.
Always find a way. Yeah, so that's for in-field. And now if we consider, now let's set f equal to 0. Let's just look at the g alpha beta, okay? So now let's look at g alpha beta. So g alpha beta, we can write it in a slightly more transparent form. So g alpha, we can write it in a more transparent, we can write the form which make it a little bit more transparent. I can write it as the following. So eta mean mu, remember, is the Minkowski metric of the full space-time. And I can write this as following: x mu beta x mu with x alpha equal to x alpha, which is along the brane direction, and xa to be phi a. Okay? So if you look at this formula, you can see, so alpha beta, so this is the induced metric for some brane embedded in the full Minkowski space-time, and the x describes such an embedding. Okay? Yeah, this generalization of this induced metric formula we encountered before for the string, but right now the only difference is that now alpha beta, they runs all in the volume direction of the d brane, and then this becomes an induced metric on the d brane when it embedded in the space-time. And this x alpha equal to x alpha, it just means that when we embed it and we choose the volume direction to be the same as the space-time direction along the brane direction. And in the perpendicular direction, this is just phi a. Okay? And if you look at this is exactly that. It's exactly that because x alpha equal to x alpha, and then you just get the eta alpha beta, and then for the other direction, then you get this one. Okay? This is clear? So when the f equal to 0, so this SDBI just become delta G alpha beta. So this is precisely the volume element of the volume element of the dp brane. Okay, because this is the induced metric, and then this is just the total volume element of the dp brane. And we see this precisely is a relativistic generalization. So this is just a generalization of the Lamborghini action we wrote earlier, which is for string. Then this would be a two-dimensional area, and here you just integrate over the volume element of the whole d brane. And so we see that this Poynting field corresponding to really describes the relativistic motion of a p-dimensional object. Okay, describe a relativistic motion of a p-dimensional object. And this 1 second, this Dirac Poynting field, when you combine these two together, and magically combines these two things into a single thing. Okay. Yes.
So I recall you saying earlier that if I'd asked you said that people have a theory of, or people have played with this idea of thinking about frames instead of just for generically higher dimensional objects and strings, but no one really understood the theory of these things because the topology and geometry are too complicated.
Yeah.
So it seems to me that wouldn't you run into that same problem right here if it's indeed some generalization non-direction?
Yeah, but we don't try to quantize it. At least we don't try to quantize this action, and we know how to quantize this action. And this is just our ordinary ordinary field theory. Yeah.
I have a question. Here we must impose that the big X acts as the coordinates in the target space.
That's right. That's right.
So phi a must be kind of constant. No constant. I mean, why there should be a constant partial R?
No. If the derivative of those things are not small, then there will be many other terms. This would not be the only action. Sorry?
You said with the constant.
The partial alpha phi a equal to constant.
Oh, equals constant.
Yeah.
Also, that means.
No, what I'm saying is that if these are constant, then this is our exact string theory action.
Oh.
And when these are not constant, and then this is a leading approximation, there will be higher order terms which depend on their derivatives. And yeah. Yes.
So one thing I just don't understand. So why is it that we don't want to try to quantize anything? I mean, shouldn't it be quantized as a principle? I mean, these are like the sort of classical analogs of the things you want to quantize.
Yeah.
So what this is to say that this object that we don't really know how to quantize.
Yeah.
So we just don't do it because we don't know how.
Yeah.
I see. Okay. It's not because. Fair enough.
Yeah, you should try anything. And only those people who have succeeded in the history books. Yeah.
Okay.
Right. Yeah, only people who have won the battle, they're in the history books. And if you just fail the battle, you are not in the history book. And so people won't tell you they have, so people have tried this but failed it, but that won't be written in the books.
Sure.
Yeah.
Sorry, maybe I missed this. So you get the square root by summing over all the massive terms in the.
Sorry?
You get the square root term by summing the series including massive terms?
No, this is still the gauge field and the phi.
Right, so how do you get it? Like, what's the series that you're summing? What's the series that you're summing?
I'm just saying in the string theory, typically you don't stop at f square. You have f cube, f4, etc. You can sum all them together. Yeah, even for the massless mode, these are just leading terms. And these are the terms with the smallest number of derivatives. And so they dominate at low energies. They dominate at low energies. But in general, even when you, even just for the effective theory of massless mode, you can have many other terms. Yeah.
I have a question.
Yeah.
Say if we assume that partial alpha phi a is constant, then we can solve out the phi a is proportional to x alpha. But how can you there assume they are just the coordinate in target space?
No, this is a function of alpha.
Yes, but why? Since it's a function of x alpha, why it can be regarded as the coordinate in target space?
Sorry, I don't understand.
All the coordinates should be independent in target space.
Sorry, I don't understand. They are independent. No, these are the worksheet coordinates. These are the world volume coordinates of the D-brane. And these are the target space coordinates. I'm just choosing the function of the target space coordinates. I'm choosing here just to be identical to the worksheet, world volume coordinates. And this one I choose to be some function of the world volume coordinate. Of course, I can do that. Any other questions? So again, this highlights that D-brane is really a dynamical object. In fact, they move, depend on the, they can move, at low energies they move like non-relativistic motion. And they actually move relativistically, say if you give enough velocity, etc. And so yeah, so because of the fluctuations of the D-brane, they become really a full dynamical object. So they have a mass, they can move around, and now you can deform their shape. Just if you have enough energy, you can bend them, etc. You can do whatever you want. Okay, so let me mention one last thing. So you may ask why somehow those fields which describe the motion of the D-brane, they corresponding to the massless modes on the world volume, of the D-branes. Whether this is a coincidence or whether, just why somehow happens to be the massless modes which describe the motion, the massless modes on the D-brane which describe the motion of the D-brane. Okay. So this is not accident. This is not accident. The reason is that so the massless, so the motion. So the Y mode describing motion of D-brane appear as okay. So this is not accident. The underlying reason is because the underlying Minkowski space is translation invariant. Okay. It's translation invariant. So that means that no matter where you put the D-brane, should be a well-defined configuration. Okay, should be a well-defined configuration, no matter where you put on the D-brane. Then that means that the low-energy effective action for the phi cannot contain a potential term. There cannot be a potential term. There should not be, say, somewhere is a minimum, somewhere is a maximum. Cannot happen. So everywhere must be the same. So means the dependence on phi can only be derivative. Can only depend on derivatives. And of course, at low energies, if you have derivatives, then can only be the massless particle. So translation invariant. So this means that any phi a equal to constant should be allowed configurations. Okay, so cannot be. That means cannot be not have potential. So max term is like a potential for phi. Okay. So to say it in the fancy words of quantum field theory 2 or quantum field theory 3, that the phi a, in other words, phi a are the Goldstone bosons for breaking translation symmetry. Okay. So previously, Minkowski space is translation invariant. And now if you put the D-brane there, then you break that translation symmetry. The location of the D-brane breaks that translation symmetry. But you can put the D-brane anywhere. Then that means the modes, the dynamics controls the location of the D-brane must not have any potential, can only have derivative terms. And so in other words, when you put the D-brane in, you spontaneously break the translation symmetry of the underlying Minkowski space. So let me mention one thing, then we can have a break. I'll mention one quick thing. So let me say a few words on the strengths of the open string interactions. So previously we described that the closed string, they interact, say by such joining and splitting procedure. Okay, and the strength here is captured by GS. Okay, So the string, so the closed string coupling is essentially the GS, which describes such a process. So if you have an open string, of course, you have a similar process. The string ends join together. You can join string ends together. So here you really just have open string. So now these lines are the boundaries of open string on the endpoint of open string. So you have two open string joined together form another one. Okay, so let's call this interaction GO, describing the interaction of the open string. So the question is, how does this GO relate to GS? Okay, and there's a simple way we can figure it out. So let's consider the simplest situation. Just have an open string propagate in time. So this is again, this is two boundaries of open string. We just propagate in time. Okay. And now let's consider a more complicated process. So the open string propagate in time. So this is just a simple surface. Okay, with two, with one initial open string and one final open string. And let's consider slightly a complicated process that we have a hole in the middle. Okay, so now the string worksheet is like this, just this part. Okay, we have a hole in the middle, and this is allowed a configuration to have some initial open string propagate to some final open string. Okay. So now we know just by counting we did before, described here. So here we're adding one boundary. Means we should add so this add a boundary. So that means we must add a factor of GS. Okay, because from this formula, this is G minus chi, and the B chi is minus B. So if we increase one boundary, then you increase the factor of GS. But we can also view this diagram as a single open string come in. Then the opposite of this splits into two open string, and then they close together. Then so they have Q, so one split operation and the one join operation. Okay? So that should correspond to GO squared. Okay? So then this means that we conclude that GS must be proportional to GO squared. That the open string coupling strength is the square root of the closed string interaction. Yes?
What's the strength of the process when closed string becomes open string and vice versa?
Sorry?
What's the strength of the process when closed string becomes an open string?
Right. Yeah, you can consider such process. Again, you can just do it by counting the topology of the surface. Yeah, such process can use this. Okay, then let's have a short break, and then so what time is it? It's 38. When should we start again? 41? Okay, 41. Yeah, let's start 41. But still, and we have already seen some remarkable aspect of the deep brain, including this channel duality, which the closed string diagram can be considered as an open string loop. The closed string exchange can be considered as an open string loop. And now we are going to see a lot of magic of the deep brain. And this comes when you put several deep brains together.
قال سنرى الآن ماجيك سحر للديب برين. طبعا هذه الحلقة ستكون يعني فيها كثير من المفاجآت، كثير جدا من المفاجآت، وقد مهدت لها في حلقة خاصة يعني سنرجع إليها إن شاء الله عندما نصل الجزئية الخاصة بها. لكن هو يقول أن هناك ماجيك، سحر في الديبرين. طالما أن هنالك ماجيك فهذا يعني أنني سأستبشر خيرا أن هذا الماجيك وهذا السحر سيتصل مباشرة مع نظريتي. ولهذا أنا يعني أقول لكم بما أنه قال هناك سحر، أنا أقول لكم أيضا هناك سحر في نظريتي. انتظروا شوفوا ماذا يقول. تعالوا نشوف.
Okay. So normally, say our conventional intuition. Say if you find some particle, say in this case, you find the deep brain. Say if you put two particles together, nothing much really changed. It's a two particle. Put three particles together, it's not much change. It's a three particle. Okay. But turns out when you put multiple deep brains together, things change a lot in a very profound way.
أول نقطة في السحر إنه إذا تقارب الديبرين يعني أن الأمر يتغير يعني كأنه يقول الفضاء يتغير بدرجة كبيرة. وذكر أن البارتيكل إذا جبنا جسيم وضعناه جنب الجسيم يعني هو معنى لا شيء يتغير. في الحقيقة السحر لنظرية علي يوسف أنه في الفضاء القريب جدا من الجسيم البارتيكل فإن الفضاء هذا يتغير، مثل ما سيقوله بعد قليل عن الديبرين ينطبق على البارتيكل. والبارتيكل أقصد به بروتون، إلكترون، كوارك، أقل من كوارك، حتى نيوترينو. فهذا هو السحر نظرية علي يوسف. تعال نواصل نشوف كيف يغير الديبرين الفضاء حوله، وطبق الأمر في نظرية علي يوسف مباشرة دون أدنى شك. فقط أن الفضاء يكون محيطا بالجسيم. يعني مثلا الإلكترون البروتون نسبة قطره 10⁻16. إذا نحن نتعامل مع فضاء محيط بالبروتون 10⁻16. يعني الإلكترون 10⁻20. إذا نحن نتعامل مع فضاء نسبة قطره دائرة، نسبة قطره أو كرة نسبة قطره 10⁻20. يعني أعلى قليل، أكبر قليل من قطر البروتون وقطر الإلكترون وقطر الكوارك وقطر النيوترينو. هذا ما أريدكم أن تركزوا عليه. الآن تعالوا نشوف ماذا يفعل الديبرين ونطبق الأمر في الفضاء المحيط بالجسيم.
So now let's consider just two deep brains. So let's consider two deep brains. Okay, so let's consider example. So let me first just tell you the naive intuition. We say suppose you have deep brain 1, deep brain 2. Okay, so for this one we have U1 gauge field. For this one, you have U1 gauge fields. Okay? Because each one we have a gauge field, a Maxwell. When you put together, from conventional wisdom, you say maybe I just have 2 Maxwell. Okay? From conventional wisdom, you have 2 Maxwell. Naively, if I put them together, I just have 2 Maxwell, right? 1 plus 1 equal to 1. Or 1 plus 1 equal to 2. 1 plus 1 equal to 2. But in string theory, 1 plus 1 equal to 4. Well, it's actually equal to 2. It's also equal to 2, depending on how you think about it. Anyway, one way to think about it is that 1 plus 1 becomes 4. So to see 1 plus 1 become 4 is very easy. So let's consider these 2 branes on top of each other. But in order to distinguish these 2 branes, I just separate them a little bit, but you should really think of them on top of each other. And so now you have 4 types of strings. You can have string going to 1, 1, going to 2, 2, then going to 1, 2, going to 2, 1. So 2, 1 and 1, 2 are different because they are oriented string. So I put the arrow there. So this is from 1 to 2, this is from 2 to 1. Okay? So we have 4 types of strings. 1, 1, 1, 2, 2, 1, 2, 2.
Why is oriented? I mean, why the 1 to 2 to 1 are different?
It's because of the one for this string sigma 0 here, for this one sigma pi there. Yeah, for this string sigma 0 there, and for this one sigma pi there. Let me just elaborate on this point. So suppose I have a string like this. Then this string is sigma 0 point ending on 1, sigma equal to pi ending on 2. But if I have a string like that, then it's a sigma 0 ending on here, and sigma equal to pi ending on there. Okay? So you have 4 types of open strings. And now if you think about how we quantize those strings, and the 4 types of open strings, they actually have identical spectrum. Because for all of them, the boundary conditions are exactly the same. Because the boundary conditions only know the location of the D branes. So all 4 types of open strings have identical spectrum. Okay? So in other words, each string excitation say this is the state on the worksheet, each state becomes 4 states because I can label ij by, so now suppose I use I and j to label 1 and 2, then I and j can be 1 and 2. Okay? So depending on whether this is 1, 1 string or 1, 2 string or 2, 1 string, 2, 2 string. Okay? So this is what I said 1 plus 1 equal to 4. Because naively, you would say I have 2 massless modes, but now I have 4 because, For example, the massless modes so each massless mode becomes 4 copies of them. Okay? Become 4 copies of them. In other words, you can think each open string excitation becomes a 2x2 matrix. Okay? I can use 2 index to label them.
طبعا هذا الأمر بسيط جدا في نظرية آل يوسف. 1 زائد 1 يساوي 4، لأنه كتلتين تقاربت مع بعض فإن تأثيرهم سيكون أقوى، وبالتالي سيكون تشكلان تهديدا أكبر للفضاء سلالات بكل هذه البساطة. بالتالي نجد أن الفضاء الخاص بالسترينج يتغير بسرعة جدا كلما تقربنا من السترينج، وهذا ما توصلت إليه في نظريتي. يعني يمكنكم أن تأخذوا كتب الحلقات 34 و 35 أيضا 36 و 37، بحيث أنه بالقرب من الكتل تتضخم. يعني كمية الكتلة تعتمد على الملاحظ، يعني تعتمد على قرب وبعد الملاحظ وهكذا.
In particular, for example, the corresponding fields, so each string excitation corresponding to some fields. For example, the gauge field associated with these now have two index ij, and similar with phi a ij. Okay? Of course, this generalizes immediately to if you have n branes. If you have n branes, then just become n times n matrices. So 1 plus 1 plus 1 to n become n squared. Okay, so now let me give some remark. So this matrix structure turned out to be, again, very, very profound. So now let me give some remark. Some remarks. So the reason. So there is a reason I call. So this is something with a two index. It's a two index. So of course you naturally to call it a matrix. But there's another reason to think about these things really as a matrix. It's because the strings, as we were doing there, the open strings they interact by joining their end. So this naturally leads to that when those strings interact with each other, and those parts naturally just emerges as a matrix product. Okay. Ij indices. Okay. So it's easy to see. Say, yeah. So let me just draw that. Yeah, let me just do it here to save some time. Suppose this is I. This is J. So this is sigma equal to 0, sigma equal to pi, and the sigma equal to pi and join with sigma 0 to n of the other one. But of course, if you want to join them together, their J have to be the same. So this is K. Then you go to I. Okay, and when they join together, then you sum of all possible J's, and then this is just like a matrix product. Okay, and yeah, so if I draw it in the diagram, not very well. So now let me separate ijk to be three things, but they don't have to be separated. Ijk can also be the same. But in order to emphasize this picture, is that you have a string to go from I to J. Okay, so let me suppose this is I, this is J, this is K. Go from I to J. Then from J to K, j to k. So sigma 0, sigma pi, and the pi end join with the sigma 0 end, and then here you get the string from so that diagram roughly can also be think as a diagram like this. Two a string join into one string with index I and k. Okay, and I, j, k can all be the same. I just make them different just to make it clear. Okay, and of course in this when you join j together, you have to sum of them because they can be in principle in all possible j's. Okay, so that actually appears as a matrix product, just follows by the nature of string interaction. And now there's another remarkable thing. Is that if we can see the phi a, so the same thing applies for A alpha or applies to any field. Is that 1, 2. So this corresponding to a string with sigma equal to 0 at 1. And sigma pi at, so this corresponds to a 1, 2 string, okay? And then this, then I can also think about the 2, 1 string, okay? So it turns out that these two can be considered as a complex conjugates of each other. Okay. For the following reason. Again, now let me just again separate this 1 and 2 so that to make it clear. So this is a 1, 2 string. So this is a 2, 1 string. Okay. So I claim string interaction defined by this way. String interaction defined by this way have the following symmetry. So string interaction described by joining the end or split the end have the following symmetry. Okay, is that I can associate each brane by a phase factor say exponential I theta I. So I labels the brane and theta can be some different, can be a phase factor. And now the rule is that if the sigma equal to 0 and on that brane, then I multiply by the exponential I theta I, and sigma equal to pi end on that brane and on I. Yeah. Let me write more expression. So if sigma 0 ending on I, then I multiply by a phase factor exponential I theta I. And if it's the sigma equal to pi end ending on I, then I multiply by exponential minus I theta I. Okay? So let's consider this operation. And the claim this operation is a symmetry of the string interaction. So let's first consider if you just have a single brane. So if you have a single brane like this, then just nothing changes because you multiply one end by I theta, the other by exponential minus I theta does not change. But now if you have such kind of interactions, because the sigma 0 and the sigma pi and sigma 0 end join together, and they can only join if they're ending on the same brane, then those factors always cancel each other. And so this would be a symmetry. Okay? So is this clear? So under this operation, phi A, say ending on the same brane, is invariant. Okay? And the phi A ij then transforms by a phase factor theta I minus theta j on phi A ij. And the phi A ji transform as a factor minus I minus theta j. Okay.
طبعا أيضا هذه أحد المفاجآت. يمكن أعتبر سيتا عبارة عن طاقة، وبالتالي أو الأيجن ستيت اوف انرجي. بالتالي إذا انتقل السترينج من أبعاد أقل إلى أبعاد أكبر فإن الطاقة تتغير، مثل الفوتون بالضبط، مثل ما يحدث للفوتون بالضبط أو الإلكترون. إذا انتقل من مدار إلى مدار طاقته تتغير، من مدار أدنى لمدار أعلى فإنه يمتص طاقة، ومن مدار أعلى لمدار أدنى فإنه يبعث طاقة. نفس الأمر ينطبق على السترينج نتيجة لتغير الطاقة. ستقول لي كيف يعني هذا لا يتناسب مع هذه المحاضرات؟ أنا لا أتكلم عن هذه المحاضرات، أنا أتكلم عن نظرية يسمى. كما قلت أني لدي مفاجأة لكم، مثل هذا البروفيسور قال لدي مفاجأة، أنا مفاجأتي هكذا. فالسترينج والإلكترون وكواكب المجموعة الشمسية والأكريشن ديسك بالنسبة للثقب الأسود كلها تندرج في نظرية واحدة اسمها نظرية يسمى. لا يوجد حدود فاصلة، لأن النظرية تتعامل مع الفضاء، إذا لا توجد حدود فاصلة في الفضاء، إذا كلها تنطبق في نظرية واحدة، وبالتالي ميكانيكا الكون، فيزياء كلاسيكية النسبية العامة كلها تدخل في نظرية يسمى، لا فرق.
So we can actually think of them as complex conjugates. Okay? So they transform in the opposite way under this phase change. Yes?
And this is because we're considering it PU1.
Sorry?
Is this because we're considering it PU1?
No, this is a good point. I will talk about this more. Yeah, just right now, let's think about each brane separately. Okay?
I have a question. In principle, can we write the interaction of open string with the, say, not a JJ, but I mean random number?
Sorry, what do you mean by random number?
Say it's I, J, K, L, but we...
No. The string can only join together if they're ending on the same brane.
Oh.
Yeah, so the J have to be the same. Yeah, so this guarantees that this will be a symmetry. Okay, good. So in this sense, they're complex conjugates. And now we can build on this a little bit further. So this actually works. Doesn't matter whether the brane are coincident or not coincident, okay? And this is generally true. So now let's consider all the branes are coincident with each other. So for coincident branes, since branes are indistinguishable from each other, so they are high-dimensional generation of what we call identical particles. So if they are indistinguishable from each other, we can shuffle their indices. We should have the symmetry to reshuffle their symmetries. So whether we call this one 1 or this one 2 or this one 2 or this one 1 should not matter. Okay? So if I combine these two observations together, then when we have n coincidental branes, then there is in fact a UN symmetry. Is that string interaction, all string interaction is invariant. Say if I have psi ij goes to say uik ujl star psi psi kl. Okay. So by acting on U just corresponding to I reshuffle all the indices. So I have to do the same U. So I reshuffle the two indices in the same way. But I have a star here. It's because of this reason. Because of this, in some sense, the sigma 0 and sigma pi, they're only symmetries if I multiply opposite phase factor. Okay. I can rewrite this as a matrix notation. If you think about each psi is a matrix, then this is a symmetry corresponding to psi U. Psi diagonal. Okay? And the U can be arbitrary, unitary matrices. Okay. So in fact, when you have n coincidental brane together, there's a UN symmetries for the string interactions. Okay? So to say it in the more fancy mathematical language, is that each open string excitations transform under the joint representation of this UN. Okay, so this is like a joint representation. If you have a UN symmetry, then this is like a joint representation. So on the worksheet, on the string worksheet, this is really a global symmetry. So it's just a phase factor associated with each end. Okay, there's nothing. It's a global symmetry. But the remarkable thing is that in the space-time, this becomes a gauge symmetry. So this tells you, because of the presence of this UN gauge symmetry, and because of each mode transform under a joint representation of some UN, that they, as a space-time field, they also must transform under a joint representation of some UN. And interpreting the space-time, then this UN must be a gauge symmetry. Okay? On the worksheet is a global symmetry, but in space-time, so let me just write it down. In space-time, or in other words, in the word volume theory of this, in the word volume of deep branes, this UN must be a gauge symmetry. for the following reason, because the only way we know, for example, this gauge field become transformed under a joint representation of some UN field, a joint representation of some UN symmetry, a joint representation of some UN symmetry, and all the excitations will have this symmetry. And the only way we can make sense the gauge field under such symmetry is that this is the gauge symmetry, and this is the gauge boson for that symmetry. Okay, is it clear? So let me just say it in words.
طبعا من خصائص الجيج بوزون أنها ما هي خصائص الجيج بوزون؟ أنها لا تخرج إلى الماس شيل، يعني WZ تكون دائما أندر ماس شيل، أي لا نكتشفها كجسيمات، وإنما فقط كطاقة تعطي الكتل للجسيمات. وهذا واضح أنه تقارب الدي برينز مع بعضها البعض، تقاربها مع بعض البعض وتحمل كتلة عالية، هذه الكتلة التي تحملها الدي برينز، فإن الفضاء بينهما يكون فضاء كثيف. يعني ارجعوا إلى كتابي حلقة 51 عندما تحدثت عن WKB adopting WKB تبني WKB وconnection field، وأرجع إلى أيضا الفيديو الخاص بالكوفاريانت برينسيبل، كوفاريانت ديريفيتيف برينسيبل. هناك فضاءين، فضاء كثيف وهو الفضاء المليء بالمجال مثل الفضاء الداخلي البروتون، والفضاء يعني المحيط بالكوارك، والفضاء الداخلي الذرة، هذا فضاء كثيف. وفضاء ليس بكثيف هو الفضاء مينكوسكي أو الفضاء الذي نحن فيه. فعند التفاعلات الصغيرة جدا، التفاعلات الجسيمات الأولية عند المفاعل الهيدرونات الكبير، فإن الفضاء هناك كثيف جدا، وبالتالي تظهر البوزونات هذه وتعطي الكتل، ونجد الكتلة خرجت من الفضاء. طيب ماذا يعني هذا؟ يعني هناك تكدس عالي جدا للطاقة، وهذا ما يحدث عند تقارب تو برينز أو غشائين من بعضهم البعض، يحصل مثل هذا. ولهذا قال المحاضر U1 جيج سيمتري، وبالتالي تنطبق عليه قوانين الجيج رولز. طيب استمر.
Must be a gauge symmetry, and in particular A alpha ij must be corresponding gauge bosons. Because this is the only way we know how to make sense. Because this is the only way we know can happen at low energies. Some gauge fields transform as a matrix, interact with each other, and this can only be Yang-Mills theory. And if this is Yang-Mills theory, then this must be a gauge symmetry. Okay? So this is the basic argument. And at low energies, we must have Yang-Mills theory.
Yang-Mills theory يعني WZ بوزون، هذا ما تفسره Yang-Mills theory. WZ بوزون. في الفضاء الكثيف الكتلة صغيرة والطاقة عالية، مثل الكوارك في فضاء كثيف الداخل البروتون كتلة صغيرة وطاقة عالية، بحيث أنه 3 كواركات تكفي البروتون كله، برغم أن البروتون طاقته 1 جيجا، والكواركات 3 كواركات لا تفوت 10 ميجا. 10 ميجا والفرق بينهما 100 جيجا، 100 ميجا، يعني 100 ضعف، الفرق بيناتهم 100 ضعف، وبالتالي 3 كواركات فقط كافية جدا أن تملأ الحيز للبروتون. إذن طاقة عالية للكواركات وكتل صغيرة للكواركات في الفضاء الكثيف. طيب الفضاء غير كثيف طاقة قليلة وكتل عالية. ماذا يشبه هذا الأمر؟ ماذا يشبه؟ الفضاء الداخلي للثقب الأسود نفس الأمر ينطبق عليه، نفس الأمر، طاقة عالية وكتلة صغيرة. طيب ماذا يشبه أيضا؟ شيء في غاية الغرابة، شيء في غاية الغرابة، يشبه الفضاء الخالي من الكتل. فضاء خالي من الكتل، معدلات تدفق زمن عالية ومعدلات تدفق مكان عالي، وبالتالي طاقة عالية وكتلة صغيرة. وأين نجد هذا؟ نجد هذا في الفضاء بعد المجرات الذي نسميه المادة المظلمة. مادة مظلمة، كتل صغيرة، قوة أساسية 3 لا تعمل، طاقة عالية أو معدلات تدفق زمن ومكان عالي، وبالتالي لا نرى تفاعلات مع الضوء، لكن نرى تأثير الجاذبية بسبب الطاقة العالية، تأثير المادة المظلمة. وهذا ما سيقوله بعد قليل هذا المحاضر، لكن لن يقول تأثير المادة المظلمة، ولكن سيتحدث عن الديب رينز ويفصل عنهما مسافة، وهذه المسافة تخبرنا يعني ستكون شبيهة بالمادة المظلمة. تعالوا نشوف.
So something remarkable happened. Something remarkable happened. So each deep brain, when we separate them, is a Maxwell theory. When we put them together, they become Yang-Mills theory. Okay, they become Yang-Mills theory, and somehow they become non-abelian. Okay.
Maxwell theory يعني تفاعلات الضوء مع المادة. ماكسويل ثيوري تفاعلات الشحنة مع الضوء، وبالتالي الجسيمات تظهر خصائصها، وبالتالي كلما تقربنا من المجرة كلما ظهرت خصائص المجرات، خصائص الجسيمات، كلما بعدنا من المجرة كلما اختفت خصائص المادة. هذا بالضبط ما تقوله نظرية اليوتيوب. كلما بعدنا من الديب رينز، بعدنا الديب رينز من بعض من البعض، تتحول الفضاء إلى فضاء داعم لماكسويل ثيوري، وكلما تقاربت الديب رينز من بعضها البعض الفضاء أصبح مقاربا ليانغ ميل ثيوري التي تتميز في أنه الجسيمات لا تظهر كتلتها وإنما تظهر طاقتها فقط، وتلك العكس تمام، تظهر كتلتها وطاقتها تكون داخل كتلتها في الفضاء المتباعد من بعض البعض.
And everything comes from, in the very trivial way in string theory, you just count the indices, but the physical implication is profound. Okay. And this can be confirmed again by just studying the explicit string theory scattering amplitude. Okay, you can calculate the scattering of 3A in string theory. Then you find it's precisely at low energy, precisely given by the same vertex as the Yang-Mills theory, etc. Okay, so you can do that. Then you find the low energy effective action can be written as the following: some Yang-Mills coupling, trace. So let me just write down the Yang-Mills theory. Times, yeah, times. Yeah, you find a low energy effective action can be written in this form. So this is standard Yang-Mills field strength, because not everything is a matrix, okay? Everything is a matrix. And both A mu, A alpha, and phi A now are n by n matrices.
Allah Akbar, Allah Akbar.
Okay. So
Allah Akbar, Allah Akbar.
So this G Yang-Mills is the Yang-Mills coupling, which describe how the gauge field interact with each other, and then obviously they should be related to the open string. Obviously this should be related to the open string interaction, because I think I have already erased it, and this kind of interaction joining the string, this is controlled. This kind of a three vertex, this corresponding to two strings joining into one string, and this proportional to GO, and this from field theory point of view, it just controls the interaction of three A's, and so that must be the Yang-Mills coupling. So this must be the Yang-Mills coupling, and then this should be related to GS to the power 1/2, which we just derived slightly earlier. So now on dimensional ground, then G Yang-Mills square can be written as, let me write it here, this is an important formula. So on dimensional ground, the G Yang-Mills square, I should be able to write it as GS. So on the Yang-Mills coupling, so we will use the standard convention that A have the dimension of mass, okay? And then this is a dimension 4 object, and this is a dimension p plus 1. And so the Yang-Mills coupling, you can deduce what is then you can deduce the dimension of the Yang-Mills coupling there. And it just turned out to be p minus 3, okay? Length. And again, because alpha prime in string theory is only length scale, so you can so the alpha prime must come from here. And then times some constant. So again, dp is just some numerical constant. Okay. And you can see explicitly that when p equal to 3, then you have a D3 brane. Then the volume theory is 4-dimensional, and then we recover that in 4 dimension, Yang-Mills theory is dimensionless. Okay, QCD coupling at tree level is dimensionless. Okay. Good. Any questions? Yes.
What to do with phi 8? What to do with phi 8?
What to do with phi 8? What do you mean what to do with phi 8?
Scalar colored particles?
Yeah, they're colored particles. I forgot to mention here is the standard derivative, covariant derivative. Yeah, so the alpha phi A is just the standard partial phi A minus, say, A alpha phi A. So it's the standard gauge covariant derivative.
Shouldn't phi be the fundamental presentation?
No, everything is to the joint, because every string have two ends.
So how to interpret phi then, from the present zoology of particles, but with 5, the one observed particles.
Sorry?
If A is just like gauge boson, like gluon or something,
Yeah.
what is 5?
Phi is some scalar field transformed on the joint representation of the gauge group. It's a matter field. Describe the motion of the brain.
Question.
Yeah.
There you say that we can reshuffle their indices. So that symmetry should be permutation symmetry? Why,
No.
Why is it?
No, you can by reshuffle, of course, I say it in the more heuristic way. But normally, if the indices is not these are the states, and you can just linear superpose them. A different I, they should be the same thing. Yeah, they just corresponding to relabeling. I'm just saying. Yeah, the lateral action of anything on the state, of course, is a unitary transformation.
Is there anything to do with that?
No, that thing is.
What are you doing?
No, that thing is related to this star. Why we put the star here? Yeah, that is. This is related why we put the star there, because the two endpoints they should transform in opposite way. Yes.
Since the brains become dynamical, can't they like fluctuate in different ways and so no longer coincide?
Sorry.
Since the brains are dynamical,
Yeah.
like you put them all in one place at first, but can they now start fluctuating and separate?
Oh, they can certainly. They can
No longer symmetric. They become distinguishable.
They can certainly start moving apart if you give them some initial motion, but the fluctuation, the system is isotropic. There's no place for them to. They will fluctuate, but they will still at that point on average. Yeah, there's no preferred direction for them to go unless you give them a direction. You say, I want them to go in that direction, then you push them.
But you can still think of them like fluctuating kind of separately, separating in their fluctuation.
Sure. No. These A are their fluctuations. Phi are their fluctuations. The phi are their fluctuations.
Is this commutator term allowing the effective action of the interaction between the D brains? Or is it?
Yeah, this is a good action, a good point. So, let me just comment on this term. So if you think about it, as we said before, a D brain, no matter what dimension of the D brain, the story when we quantize them, they are almost the same. It's the same spectrum. It just depends on. Say if you have a space-filling brain, then everything is A alpha, and then if you have some lower dimensional brain, then some of them become scalar field, etc. So essentially, they all have the same dynamics, and so this interaction can be considered. It just comes from here. So you can start with space-time filling brain, and then you go to lower dimensions, and then this just can be considered come from there, right? Yeah, it's part of the gauge theory. Yeah.
So the whole low-end action is like the action of zero gravity plus the action. You can think about the whole low-end action.
Oh, you mean if we include the closed string?
Yeah.
Yeah, that's right. If you have D brains, that's right. This is the effective action on the D brain. This is the effective action on the D brain.
I mean, if you think D brain as a solution, right?
Yeah.
Then here that is action.
No, that's what you said.
Yeah, that's the two actions cross together.
Yeah. Good.
Excuse me. How come we have a term in action that's proportional to phi without derivative?
No, they are derivatives. This is covariant derivatives.
The commutator.
No, but phi have covariant derivatives.
So the next one.
Yeah.
Yeah, that thing is usually proportional to phi without derivative.
Yes.
So what isn't it?
Ah.
Minkowski's phasors.
Yeah, that's a very good point. I'm going to mention that point. Yeah, but the key is that this particular potential term. Yeah, this is a very good point. I'm going to mention that. Yeah, I will mention that in a few minutes. I do, because I do want you to do your P-set. So now let's consider separating the brain. Now let's consider the separating the brain.
الآن سأتحدث عن انفصال البرينز من بعضهما بمسافة دي، وتذكروا أنه يعني إذا انفصل البرينز من بعضهم البعض فإن المعادلة ستتحول من ياغميل ثيوري لماكسويل ثيوري، وبالتالي تظهر خواص الجسيمات، وهذا ما يسمى بتأثير المادة المظلمة. المادة المظلمة لأنه قرب البرينز مع بعض يعطينا فضاء مثل الفضاء الثقب الأسود داخل الثقب الأسود، ويكون فيه تايم كونتراكشن وسبيس كونتراكشن، وأيضا يشابه هذا الفضاء هو فضاء عند الأبعاد الصغيرة برضو يعني تايم كونتراكشن وسبيس كونتراكشن، وأيضا عند الفضاء الخالي من الكتل تايم كونتراكشن أيضا وسبيس كونتراكشن. في هذه الثلاثة خواص أو الثلاثة أماكن في الفضاء تختفي القوى الأساسية الثلاث أو تبدأ في الاختفاء. طيب تعالوا نشوف هذا الكلام.
Let's consider the situation. We just have two of them. So at the beginning they're coincidental, and then now let's separate them in some direction. So let's call that direction x. Okay, so let's say they separate by some distance t. So this is 1, this is 2. Okay. So of course this 1, 1 and the 2, 2 string, nothing changes, because they're just still only on the same brain. But those strings are now different. So now 1, 2 or 2, 1 string become different. So 1, 1, 2, 2 exactly the same before. And the 1, 2 string, for example, let's consider the 1, 2 string. Then the boundary condition changes. In the way I have sigma equal to 0, say in the x direction. Sigma equal to 0, tau, say it's at some location, say let's call this x0. And then x sigma equal to pi, tau, then become x0 plus t. Okay? So now it means when you quantize this string, you have to do a slightly modified boundary condition. Say you have, say it starts with x equal to 0. Now you must include the term depend on sigma. Okay? And again, as before, we take the xl to be minus xr and the periodic, etc. And then in order to, so for sigma equal to 0, then this boundary condition is satisfied. But in order to satisfy the boundary condition at pi, then you now need this w equal to d divided by pi. Okay? Okay, you need to develop d divided by pi. So now you have a sigma term, so that will change your mass shell condition. So remember the mass shell condition we have before is something like this. Q alpha prime p minus, say is p plus 4 pi alpha prime. Say for the open string, I'm writing the open string version, which is up to some numerical factor the same as closed string we wrote down before. So now because because of this term, then there's additional contribution on the right-hand side. Okay, it makes sense because now string have to be stretched over some distance that costs energy. So take you 1 minute to do it yourself. I just plug this into here. You only need to look at how the behavior of this term. Just plug in there. Take you, say, 5 seconds. You find that the mass condition now have one more term plus the rest as before, and that means now the previously massless particle, this here with the corresponding A alpha and phi A are no longer massless, because previously they're massless because those terms are 0, but now you have one more term, and they have a mass given by m divided by d divided by 2 pi alpha prime. Just take the square root of that. And of course, this is precisely the d times the string tension, because 1 over 2 pi alpha prime is the string tension. So this is exactly the energy you expect just from a classical picture. You have a string stretched between the two, then just the tension times the length of the string. Okay? So now you can also easily understand what's going on from field theory point of view. And now you only have two massless modes, two sets of massless modes now, rather than 4. So what's happening is that now the gauge symmetry is broken from U2 to U1 times U1. Okay? U1 times U1.
هذا ما ذكرته ينكسر من U2 تايم U1 اللي هو يتحول من يانغ ميل ثيوري و WZ بوزونز إلى ماكسويل بارتكلز اللي هو تفاعلات الفوتون مع الإلكترون مع الشحنة يعني عموما، سواء كان الإلكترون في الذرة سواء كان، وهذا ما يحصل تأثير المادة المظلمة. فقط مشابهة بالمشابهة، فقط مشابهة الفضاء داخل الثقب الأسود مع الفضاء حول المجرات، لأن المجرة كلما بعدنا من المجرة كلما زاد التايم كونتراكشن وقل التايم دايليشن. بالمناسبة أنا قدمت فيديو في هذا، تعال نمشي نشوفه. قدمت فيديو، هذا الفيديو من أجل التشويق لمتابعتي اكتشفت للتو أن نظرية الأوتار تتفق معي في أنه لا يوجد ما يسمى بالمادة المظلمة. هذا الفيديو الذي مدته 20 دقيقة فاصل 8 ثواني. في هذا الفيديو أنا تحدثت بشكل مختلف قليلا من الآن أشرحه أنا، لكن في النهاية وصلنا لنفس النتيجة. قدمت الأمر بشكل مختلف لكن وصلنا على نفس النتيجة، لأنه كان ذلك في المسحة الأولى أو النظرة الأولى الأوفر فيو، يعني النظرة العامة الأولى، والآن في نوع من التدقيق في الأمر. لهذا كانت يعني النتيجة واحدة لكن الطريقة كانت مختلفة من بعض البعض. طيب تعالوا نرجع نكمل الباقي.
So the separation of the brains essentially corresponding to the Higgs mechanism. In the following sense, when you separate the brain, I said before, you said phi should be interpreted as the denoting the location of the brain. when you separate the brane, that means one of the 5 fields corresponding to the x is in the transverse direction for the brane. One of the 5 fields corresponding to the x, they must develop expectation value. Okay? They must develop expectation value. And that expectation value then give rise to this mass. So this is precisely a Higgs mechanism. So now let's go back to the question. What this potential term means, whether we can actually, as we said before, because the translation symmetry, in principle we can pull the brane anywhere. Okay? And now I'm out of time. So let me just say, if you look at this potential, this becomes 0 precisely when phi A and phi B all become commute. Okay? So that means you can diagonalize the phi corresponding to all the transverse directions. You can diagonalize phi corresponding to all the transverse directions. And then they corresponding to the location you put all your branes. Yeah, go to your P set, then you will see a more explicit discussion of this. Okay? And then one final remark. He says, at the beginning you start with n brane together. And then because of this, we can separate them. So we can find a solution which, say the commute, say the set, separate them into different stacks. Okay? So N1, N2, N3, etc. So this corresponding to the configuration of phi. So this corresponding to the configuration of phi. So let me just write overall phi as a vector. Say there's A1, N1 of them at location A1, and N2 of them at location A2, and AK, okay? So if I separate it into n stacks, then it will be like this. So N1 of them at location A1, and N2 of them at location A2. We can check, so this is A1 times N1, and yeah, so this is N1 times N1, times N1 times N1 identity matrix, okay? This is N2 times N2. And you can check that this such a configuration does satisfy this condition, so that we can actually can separate brane into such configurations. And in this case, then the gauge symmetry is broken into UN1 times UN2 times UNK. Because only those coincidental parts survives. Okay? And all the other string between them become massive. Okay, let's stop here.
The following.
إذن هذا تشابه غريب جدا جدا بين نظريتي وبين السترينج ثيوري، وحتى في الخطوة الأخيرة التي ذكرها عندما شكل هذه الماتريكس وقال ستاكس يعني تنقسم المدارات، تنقسم البرينس إلى مجموعات، يعني مجموعات وتصل بينها مسافة. هذا نفس الأمر الذي ينطبق في المدارات بالإلكترونات. بالمناسبة الإلكترونات مدار الإلكترون أيضا كومباكتد، وأيضا ينقسم إلى في حالة الديجنيرسي تنقسم إلى مدارات أخرى، وكلما كان المدارات متقاربة بعض كلما لم تظهر خواص هذه المدارات. نفس الأمر ينطبق فيه، كلما تقارب البرينس لا تظهر خواص هذه البرينس، ولا تظهر خواص الجيج فيلد الذي ينتج منها. نفس الأمر ينطبق هنا وينطبق هنا واحد، وأيضا ينطبق في الفضاء البعيد جدا من المجرات، ويسمى بالفضاء بسبب تأثير المادة المظلمة، لكن هو ليست مادة مظلمة، هو فقط مادة عادية، لكن القوى الأساسية الثلاث لا تظهر بالنسبة للتدفق. هذا نسبة لأن هناك تدفقات عالية للمكان وللزمان في غياب الكتلة، وهو ما يحصل في الفضاء داخل الثقب الأسود. الأمر واحد، كله واحد. فهذه الفضاء متصل، هذه الفيزياء متصلة مع بعضها البعض، جميع الظواهر الكونية متصلة مع بعضها البعض حسب نظرية اليوتيوب. نكتفي بهذا. السلام عليكم ورحمة الله.